So with this video, we're going to go back to doing calculations. What do we mean by that? For the past few videos, we've been talking about higher fair share derivatives. Of course, there have been a few calculations, like when we proved Taylor's theorem, used the mean value inequality, all this sort of stuff. But perhaps the core of the subject, or at least the most difficult part of it, were these isomorphisms, where these kind of algebraic concepts that allow it to relate the space of K-linear transformation from V to the J-linear transformation from V to W to the space of K plus J linear transformations from V to W. So we're going to move on to something else. Eventually, or actually in the next video, we're going to start talking about some classical theorems from higher dimensional calculus, the inverse and implicit function theorems. Before we do that, we need a tool, which is the Banach fixed point theorem, which has a life of its own. And so, as an aside, besides proving the Banach fixed point theorem, I'm going to be looking at a very easy to prove, but very fundamental existence and uniqueness theorem for ordinary differential equations. Okay? So, okay, what is this theorem, this Banach fixed point theorem? Well, it's a theorem that applies to maps defined over metric spaces. So here I have a complete metric space. Well, ordinarily I'd write this with D sub x, but I'm not going to do it because I just have one space. So you know which metric I'm using. So I have a mapping, what's going to be a continuous mapping from x itself. But and then I define its iterates. Well, okay, age raised to 0 is just the identity map. And age raised to I, well, it's age composed with age I times. And of course, that's the same thing as taking age I minus 1 and composing it with age. Also the same thing as taking age I minus 1 and compose the age in the other order. And the main assumption of the theorem is this, that we have this map, and that the maps age to the I, they're all Lipschitz, with these constants here, kappa I, and the constants are summable. Okay? So you may have seen slightly different versions of this theorem, where you just assume that age is kappa Lipschitz with kappa less than 1. Here I'm making a different assumption, which somehow is more convenient for certain proofs, but as we're going to see. But okay, so my assumption is that each age to the I is kappa I Lipschitz, and that the constants are summable, of course, because age 0 is the identity map. I can take kappa 0 to be equal to 1, and I'm always going to do that. Okay? Okay, so this is my assumption. I have this map, age, and as its iterates are Lipschitz, and that the Lipschitz constants are summable. And here's a statement of the theorem. First of all, age has a unique fixed point. So there's a unique point, x star in x, that is a fixed point for age, such that age of x star is equal to x star. The second part of the theorem is that if I take any initial point x and I start applying age iteratively to x, right? So apply age to x and get age of x. Then I apply age to age of x and get age squared of x. And I keep repeating this process. So what happens in the limit is that the iterates converge to this unique fixed point here. And there is a third part, which maybe if you have seen this theorem before, it's quite possible that you have not seen part C. Part C is a way of trying to determine how close you are to the unique fixed point, right? For any x as well. You want to get a bound on the distance between x and the unique fixed point. So we know that this distance is 0 if and only if x is equal to age of x. What happens, however, is that if x is nearly equal to age of x, that is, if this distance here is small, then so is this distance. So it's like a point x that's not moved much by age, right? So a point x such that age of x is close to x must be close to x star as well. So as I like saying, any nearly fixed point is close to the unique fixed point. Okay? So, right, before we prove this theorem, I want to show you the simple application to ODEs in and actually Banach spaces if you like. Okay, so first of all, I need a definition. What's the kind of ODE that I'll be looking at? I'm gonna be looking at things like f prime of t is equal to psi of t f of t. So I need this function psi. Well, it takes as input a real number between 0 and capital T. That's going to be time for us. And V is my Banach space. It could be R, RD, anything in that space. Right, meaning that F, the solution that I'm looking for, records the trajectory of a particle moving around V, and T is the time variable. Okay, I'm going to assume this function psi is continuous. The V is Banach, of course. And also assume that this function is L Lipschitz in the spatial variable, meaning that if I fix the time, and I take 2 points in V, and I compute psi of tx minus psi of tx prime, well, this distance, this should be a norm in V, right? So psi takes values in V. So this distance is at most L times the distance between x and x prime. So it's just a Lipschitz condition, except that I'm not assuming that psi is actually Lipschitz. I'm assuming that if I fix a t, then psi of t something is Lipschitz in that something, with a constant that does not depend on t. So that's right. Okay, so my theorem is an existence and uniqueness theorem for ODEs like this. So, I mean, it's a global existence theorem, if you like. It's I'm not going to get into too many details. If you wanted to prove a local existence theorem, then you could start by assuming that psi is not defined over the whole of V, but only over an open set. You could do all sorts of things like this. But I really want to prove a clean statement that gives you kind of global existence up to time capital T. And here's the theorem. The theorem is this. Take an initial condition, right? So this is my initial condition. And I want to find a trajectory that, well, is at x naught at time 0. And with the derivative specified by the ODE I described before, right? Derivative of f, right? So this is f of x naught. So this is a function such that when you differentiate it, the derivative is psi of t f of t. And moreover, this function is equal to x0 at time 0. The claim is that there exists a unique f of x0, continuous, that satisfies this. Well, why does it have to be continuous? Because it's differentiable, right? When I write this, I'm saying it's a differentiable function. Differentiable functions are always continuous, so there's no question about that. That if there is a solution, it's continuous. And yeah, there's a unique solution under our assumptions. Moreover, we're going to prove in one go that this solution satisfies a Lipschitz property with respect to the initial conditions. Now, remember that this thing here for functions from 0t to v, continuous functions, is just the soup of f of x naught t. So I'm comparing here solutions with different initial conditions. And I ask how close or how far away can they be? And the continuity statement says that their distance can only be a constant multiple of the distance between the initial conditions, and the constant is given by this exponential. I mean, this is something that's sometimes proven in ODE classes. Once you prove existence, then you have uniqueness using some sort of Grown inequality argument. In some sense, the Grown inequality, in our case, is going to be hidden inside the Banach fixed point theorem. Right, so let's see how I prove this. Is going to be more of a sketch because it's an aside. It's not part of our main topics. It's just something I want to do so that you see how you can apply Banach's fixed point theorem in a context that's not related to the things we're going to be doing later. Okay, what's the proof, right? So as you can suspect, we have Banach's fixed point theorem is about fixed points. So I want to convert this problem P into a problem about fixed points. That is, I need to define an operator, a function, in this space of continuous functions, such that the solutions to the problem P are precisely fixed points of that operator. And I also want this operator, this function from C to C, to be continuous, or to even be Lipschitz, right? So that causes Well, that might make one ponder because we're talking about here about differentiation, which is a very discontinuous operation. So it's convenient to turn everything into an integral problem. So how do we do this? This is very classical. You must have seen it before, or many of you will have seen it before. So what you do is define this operator for each initial condition. You have tau of x naught that maps f to a new function. And this function is this. So it's a function that at time 0 is equal to x naught. And it's the integral of psi of s, f of s. Remember that psi is continuous, so it's easy to check that this is a continuous function in S. It takes values in V. And we've learned how to integrate functions with values in a Banach space. So we know how to do this. We know how to do this integral. We know that when we take the derivative here, you just have the value of the integrand at time t. And using that, you can check that a function, any function, continuous or not, but any function that's a solution to P must be continuous. But P is the Cauchy problem here. So any function that's a solution to this problem must be continuous. And moreover, it must be a fixed point at this operation. Meaning that if it's a solution, you just write this down, you take the derivative, you see it's a fixed point. On the other hand, if it's a fixed point, then it satisfies your ODE. Well, it's not hard. So I'm not going to prove this, but it's easy. Okay? So, right. So what do we have so far? I have converted my problem of finding solutions to the ODE into a problem of finding fixed points of a certain function from C to C. And now I'm going to need an estimate that's going to be crucial to everything that follows, right? So remember, in the end, if I want to apply the Banach's fixed point theorem, I need to prove that this tau of x naught is Lipschitz and its iterates are Lipschitz with sufficiently fast decaying coefficients. So as a kind of first step for that, I need this Picard estimate, right? So Picard came up with this proof of existence and uniqueness for ODEs that also shows that iterates of this operator converge to a solution. But okay, so I need to prove this estimate, and it's really simple, right? So notice that I'm not taking the soup norm here, and somehow that's fundamental. We need to save the soup for later. Okay, the soup, not the soup. Okay, yeah, never mind. Right, so how do we prove this? Well, this is just stuff, estimates that we learned when we defined this integral, that we saw in exercises, right? So remember, first of all, what is this guy? Let me move this proof here. What is this guy? Well, this is just x naught plus integral from 0 to t psi of s f of s ds. And the same for g, right? So if I take a g here, all that changes, I'm going to get a g there. Now, what happens when I take this difference? So the x naught is going to cancel out, right? So the x naught is going to disappear. It's just a constant that appears in both guys, both tau of f and tau of g, so it's going to disappear. And moreover, I'm going to get a difference of integrals, which we know is the integral of the difference. So let me write this down here. And I need a small ds and a double bar. Hopefully you can understand this. Right, so I'm just integrating the difference between sides. Well, okay, let me fix this quickly. Now I'm going to move the norm inside because I know I can, and this is just going to make everything larger. And we've argued that, okay, this integral here is a limit of Riemann sums. If I move the norm inside a Riemann sum, it can only get larger. So the integral can only get larger too. And I get this. right? And now the last step is to notice that by assumption, remember that when I have something like psi computed at a certain time and a certain x, minus psi computed at a certain time and an x prime, this is less than L times norm of x minus x prime. So this whole thing here is less than L times the integral from 0 to t f of s minus g of s. And I'm done with this estimate. So now I have my estimate, and I'm going to use it to bound the iterates of tau. So I want to remember, I want to prove in the end that these iterates are Lipschitz functions with sufficiently fast decaying coefficient, Lipschitz constants. Okay, so let's do that. My claim is that I have this Lipschitz property here. So this is going to be my kappa I when I apply the fixed point theorem. It's Lt raised to I divided by I factorial. And notice that when I add these guys up, I get an exponential of L times t. Okay, but that comes later. So just notice it now because it maybe helps you understand a little bit. So I'm actually going to prove a slightly stronger statement. I'm going to prove this by induction. That for any f and g in C, and for any I natural, including 0, that f of t, right, for any t in the interval 0 t, g of t, sorry, ti x naught f of t minus tau, not ti, tau I, x over g of t. This is less than Lt raised to I. F minus g infinity. So why is this enough? Well, maybe I'm going to leave this a little bit of an exercise. I just noticed that if I want to compute the, right, so what I want in the end is about a bound on the infinity norm and argue that this is less than L capital T over I factorial, sorry, I factorial f minus g. And that's what I want, right? So, and I claim that what I'm going to prove here, the star statement, is stronger. And why is that? Because to compute this infinity norm here, I need to take a sup over little t in the time interval from 0 to capital T. And of course, here I have little t, but this is an increasing function of little t, right? So if I take capital T, I get a bound that's still valid. So, okay, maybe you need to think about it a little bit, but I claim that this start statement is what you need, right? Okay, so how do we prove star? Well, first of all, there's a base case, which is I equals 0, and that's okay automatically. Because what do you get for I equals 0? Well, this whole coefficient here of, you're just saying that, well, tau raised to 0 is just the identity, right? So I'm looking at f of t minus g of t, and that's less than 1 times the infinity norm of f minus g. And of course, that's true by definition of the infinity norm. Now, let me look at a positive I, and that's my inductive step. I'm going to assume that the theorem is true for smaller I, that the start statement is true. And I'm going to need the estimate that I proved in the previous screen, this pK estimate. This is the V norm. So this is the same thing as computing tau. I'm looking at tau of x naught applied to tau x naught I minus 1 f t minus tau x naught I minus 1 g t. Right? No big deal. I'm just saying that tau x naught raised to I is equal to this composition here of tau x naught I minus 1 and tau x naught. And same for g. Now I can apply the Picard estimate because remember, let me go back quickly. The Picard estimate applies to if you take a function and apply tau to it, take another function and apply tau to it. And here's what I have. I take one function, well, it happens to be this function, and I apply tau to it. And take this other function and apply tau to it. And okay. And sorry, I need to insert in the page here. So by Picard, if I look at tau x naught I minus 1 x naught f of it, tau x naught I minus 1 apply g t. This is less or equal to the integral of L from 0 to t, the distance between tau x naught I minus 1 f of s minus tau x naught I minus 1 g of s. Now, great, I have I minus 1, so I'm going to apply the inductive hypothesis. The inductive hypothesis means that this thing here is upper bounded by Lt raised to I minus 1 divided by I minus 1 factorial. Sorry, L little t here. And then I multiply by the norm, the infinity norm of f minus g. And this is s, sorry, right? So I'm doing it for time s. And now I just have to integrate. So you see that from here you get L raised to I. And then you get the integral of si minus 1 from 0 to t. That gives you t raised to I. Get the integral from 0 to t of s raised to I minus 1. So you get t to the I divided by I times I minus 1 f minus g. And this is simply equal to LTI divided by I factorial norm of f minus g, which is what we wanted to prove. Right, so we use Picard here and the induction hypothesis here to do what we want to do. So okay, this proves this star statement, which I recall was just this, so that if you iterate tau I times to apply to f, and iterate tau I times apply to g, then you have this bounded difference here, this bound here. And as I said, this implies that the map tau x naught I is Lt over I factor LTI over I factor Lt to the I divided by I factorial Lipschitz. So we're finally in a position to apply Banach's fixed point theorem. Why? Remember that tau of x naught is a map between the C space, well, C0T V. It's a map from this space to itself. C0T V is a complete, it's a Banach space, so it's a complete metric space with its usual norm, the infinity norm. And now I have a bound on the Lipschitz constants of the iterates of tau x naught. These bound means that the sum of these Lipschitz constants is exactly the exponential of L times t. So the Banach fixed point theorem tells me that if I have a mapping from a complete Banach space or complete metric space to itself, whose Lipschitz constants are summable, then it has a unique fixed point. So tau x naught has a unique fixed point f of x naught. And as we noticed, this f of x naught then has to be the unique solution to that problem P, to the Cauchy problem. Okay? That's not the end of it, because I still want to show something about the difference between f of x naught and f of x naught prime. But now notice, you just go back to the definition. You note that there are different mappings for each initial condition, right? So what's tau of x naught? Well, it's x naught plus an integral. Tau of x naught prime is x naught prime plus an integral. So the difference between tau of x naught and tau of x naught prime is just a constant. It's just this vector here. What does that mean? It means that, okay, you know that f of x naught prime satisfies this. Right? It's unique solution. So it also satisfies this. right? Which means that the distance between f of x naught prime and tau x naught f of x naught prime is at most the distance between x naught and x naught prime. So you just need to check this if you like. So I remember that the last part of Banach's fixed point theorem was that if I want to know the distance of this guy to the fixed point of the map tau x0, one way to get about is, okay, I have the sum of Lipschitz constants. Then I look at what happens when I apply tau, well, I apply my mapping, tau of x0 in this case, to f of at tau of x naught, apply it to f of x naught prime, and look at the distance. And this distance by this calculation is simply the distance between x naught and x naught prime. So we're done. We've shown that by changing the initial condition, you cannot change the solution and norm by more than e to the LT, which is the sum of Lipschitz constant, times the distance between the initial conditions. So okay, now we have our existence and uniqueness and continuity theorem for ordinary differential equations. So let me just go back quickly and remind you what we have. So maybe I need to erase a few of the blue lines. I'm just saying that I have this ODE, and I've just argued that under this Lipschitz assumption, which is a strong assumption, but it's verifiable in many cases for such for linear systems, but also many other important things in life. So under the above assumptions, I have a unique solution for any time interval 0 to capital T. There's a unique solution to this problem, this Cauchy problem. And I also have this continuity property in the initial condition. So if I change x naught to x naught prime, the solution can only change by at most e to the LT times the distance between x naught and x naught prime. So it's pretty cool, right? So this very abstract and very elegant Banach fixed point theorem, which I'm going to prove right now, gives you this for essentially free. Well, okay, you have to do this Picard thing, but all right. Anyway, so let's prove the Banach fixed point theorem. Remember, the statement is I have an age. H0 is identity map. Age I is the ith iterate of age. The Lipschitz constants of the iterates are summable. So I need to prove these three things. So there's an X star missing here. And what I'm going to do is I'm first going to prove existence of a fixed point and convergence to it, meaning the following. So I'm going to argue that take any point in X. If I compute the iterates of X, these iterates converge to a fixed point. I don't know yet that it's the unique fixed point, but they do converge to a fixed point. And moreover, this unique fixed point is at a distance from X, which is bounded by this formula I gave in part C of the theorem. Right? So I don't know yet. I have to prove that there's uniqueness of the fixed point, right? So I don't know. I haven't argued that. I'm not going to argue that in step one. Rather, what I'm going to do is just start from a point. The iterates are going to converge to a fixed point, and therefore, and moreover, this fixed point is at a distance from X. Is at most what this bound here gives you. Okay? So let's prove this thing. So recall. So if I have a sequence of points, maybe indexed from 0 to infinity, satisfying that the sum of the distance between successive terms, if this sum is finite, then x sub I converges to some x, well, I'm going to call it x star for reasons that are going to be clear. And moreover, I have the following. I mean, we proved this in some previous video. If you don't remember it, it's a nice exercise. It's just to say, if I have a sequence of points in X, and this should be satisfies. If I have a sequence of points in X, I find this condition, then it's Cauchy, and therefore it converges somewhere. And actually, there's a way of getting a bound on the distance between x naught and x star, which is just to notice that this is the limit, right? X star is the limit, so this is the limit between distance of x naught, xi, well, let me call it this j. This is less than or equal to, by the triangle inequality, then the limit from j going to infinity. Instead of looking at the distance between x naught and xj, I'm going to break this into pieces. Right, so between successive terms. And of course, this gives me a sum up from, right, this gives me a piece of this sum here. So this is a part of what I have above. So in particular, when I let j go to infinity, I get the whole sum, I get the whole series here. And the series is convergent, right? So what I'm saying is that the distance between x naught and x prime has to be bounded by the limit of these sums of distances between consecutive terms. And that limit is a series. So again, what am I doing? I'm saying take an arbitrary sequence of points in x. If it satisfies this condition, then not only the sequence converges to some x star, but also the distance between the first term and the limit is bounded by the series. So okay, we're going to apply this criterion now. And what is the sequence that we're interested in? Well, that's sort of obvious, right? So remember that I want to start from an arbitrary point in x, and I want to apply iterates of my function, right? So let's look at these distances. So for any I, the distance between xi and xi plus 1, that's the distance between hi of x and hi of h of x, right? So this is just hi plus 1 of x. Why do I write this like this? Well, this is hi plus 1 of x. I want to use the Lipschitz property of hi, right? So here I'm computing hi at a point, hi at another point. So this distance at most the Lipschitz constant times the distance between x and h of x. Conclusion: the sum of the distances between xi and xi plus 1 is at most the sum of kappa I dx h of x, and because I have dx h of x a common term, I have this thing. The assumption is that the sums of the Lipschitz constants are the sum of the Lipschitz constants are finite, so this is a finite number as well. And I've discovered that x sub I, which is hi of x, converges to x star, and that the distance between x and x star, that's just using the stuff in the previous slide, this distance is less than or equal to this. Now, I want to argue also what's missing is that h star at x star is a fixed point, but that's easy. Well, x star is the limit of hi of x, which is the same as the limit of hi plus 1 of x, which is the same as the limit of h applied to hi of x. And what is this, right? So, well, this is just shifting the sequence by one term, doesn't change the limit. Now I just wrote that, sorry, this I here is misplaced. Sorry. So here I have h applied to hi, so of course that's hi plus 1. But h is continuous, right? And what's inside here converges to x star. So this is simply h of x star by continuity of h. So h is Lipschitz, therefore it's continuous. So there is no question that x star is equal to h of x star. And that's kind of a general theme that perhaps you've seen it in many previous classes or calculus even, that if you iterate a function, in this case h, and the iterates converge, then the limit must be a fixed point. It's not always true that there is a limit, but when there is a limit, then the limit is a fixed point. So just to make it clear, I mean, this inequality here comes from the stuff in the previous page. Okay, so what have we got so far by step 1? Let me remind you, we've shown that if I take a starting point, do iterates, I converge to a fixed point, and the distance between x and a fixed point is this. What is missing is that this fixed point is unique, that there's no other fixed point. Because if we know there's a unique fixed point, then okay, we know the 3 parts of the theorem, right? There's a unique fixed point, iterates converge to this fixed point because there's no other, and the distance between a point and a fixed point is bounded by that series, which we have from step 1. So okay, let's prove that there's only one fixed point. Right, so how do we do this? Suppose I have 2 fixed points and I want to show that they're the same. Let me take an I such that the Lipschitz constant of h sub I of h to the I is less than 1. How do I know that exists? Well, the sum of the kappa i's is finite. When you have a summable series, it means that the general term, in that case, the kappa i's go to 0. So there must be one of them that's less than 1. Actually, infinitely many of them are less than 1. So, okay, what is this? So I have that in fact h, well, I'm just gonna rewrite this over here, take this I, and I know that x star is also a fixed point of h raised to I. And also the same for y star, just iterating this, right? So now notice the distance between x star and y star is equal by what I wrote above, h sub I x star, not sub I, sorry, h to the I x star, h to the I y star. By the Lipschitz property, this is less than kappa I, d x star y star. And now, because I have 1 minus kappa I, right, just move this to the other side. This is less than or equal to 0. And of course, this is a positive number because kappa I is less than 1. So, what do we have here? We're saying that the distance between x star and y star has to be less than or equal to 0. Now, there's only one way in which this can happen because distances are non-negative. That's if the distance is 0, which of course implies by the axioms of a metric that x star and y star are the same point. So if I take 2 fixed points, they must be one and the same. So let's just quickly go back, okay, to the statement of the theorem. So I wanted to prove that there was a unique fixed point, that iterates converge to it, and that the distance is bounded by the series. Right. So in step 1, what we did was to argue that step 1 proves everything except for this uniqueness, right? So in the following sense, I argue that first B, that the iterates converge to something, and that something is a fixed point. So that's step 1, and also I argued this in step 1. So the only thing that step 1 doesn't do is to prove uniqueness. But I say, okay, take an x, to be more precise, right? So take an x, the iterates converge somewhere. This somewhere is a fixed point. The distance between x and that specific fixed point is at most the series. And that's step 1. So, and once we have step 1, then what is missing is to prove that there's a unique fixed point. Because given that, then we know that this x star, in principle, right? So when I write step 1, in principle, it could be that x star depends on the starting x, that for each initial x I converge to a fixed point, but these fixed points could be different. So if I start from y, I get a different fixed point. And that's what step 2 rules out. Step 2 shows that there are no 2 fixed points. There's only one. So everybody converges to the same fixed point when you iterate the mapping. And this is how we finish the proof of this very nice abstract theorem. It's useful in many contexts. We've used it to prove existence of solution to ODEs. In the next video, we're going to use it in a different way, very different way, to prove the inverse function theorem. As we're going to see, there are parts of the proof that are more or less straightforward analysis, but there's one crucial step where we need a new idea, where we really need to prove something that's non-trivial, which is to show that under certain conditions, a C1, a transformation between Banach spaces with a continuous invertible derivative maps open sets to open sets. So that's something that's going to be crucial in the proof, and that's the hard step, and that's the step where we're going to use this fixed point theorem. Okay? So, but that's it for this video, so thank you very much.